Well, if it is, then we're going to have to prove it. So here we go. Good question. So first one, what's the answer to the first one? It is 0. That should be rather straightforward. This is related a little bit to our conversation last time that doesn't the quadratic grow faster than the line, right? So shouldn't it be going then toward 0 here? So that one. Other ways to think about it, like horizontal asymptotes, agree the denominator is bigger than the numerator, right? We saw that in pre-calc. This answer is 0. Next one. Natural log of n plus 1 over n. This one's also 0. Convince me. L'Hopital's rule will prove this one. Okay, so take the derivative of the numerator, derivative of the denominator. You should have something then like this. 1 over n plus 1 over 1. It's definitely true, right? When we think about comparing the growth rates, and if I already know the growth rate of the functions, then I can answer it from that perspective. So notice that this answer is going to give us 0. It's going to be 1 over n plus 1. As n goes to infinity, the answer is 0. But notice that if we think in growth rates, that doesn't the line grow faster than the log? We saw that last time. So doesn't it then have to go towards 0 then, that fraction, as the denominator gets big? Okay. This last one is E. Do you want me to just say I told you so and move on? Good. Let's talk about why it's E. Now, let's suppose I don't know what this is. So let's say equals L right now. Okay? I'm just going to call it L. So let me actually rewrite this a little bit. So the limit as n goes to infinity of 1 plus 1 over n to the n. Now, if we're looking at this, we might be tempted to say that this answer is the number 1. Sometimes people do because they look right here and they go, well, isn't that 0? So isn't that 1? This is actually a 1 to the infinity indeterminate form. Okay? And it's not going to be 1. There's a lot of ways we know that this is not the number 1. Really obvious way that we know it's not the number 1. If you put this function into your calculator, 1 plus 1 over x to the x, right? I just changed the x's to be n's. You will see something that's doing this, that has a horizontal asymptote, at least it looks like it, at not 1. So there's something going on here that's different. And here's again why this indeterminate form is actually a rearrangement of a familiar indeterminate form. So I'm going to do that. We saw one kind of like this last time. And how did we handle it? Nene, this is actually what you were working on there. Okay, so I'm going to take the natural log of both sides. So on this side, I'm going to have the natural log of L, whatever L is, and I don't know. I'm just wanting to have that placeholder there. L is the answer to this question. And I can take the natural log of the other side. So I'm going to have, I still have this limit that's hanging around. Now the natural log is a continuous function, so I can just find the y value here in a minute. But anyway, so this. The whole point of doing that was to bring this in down out in front, right? That's a property of logarithms. I'm going to flip it around here a little bit as well, just so that the L is on the other side. Now I want to pause for just a minute and recognize that this is actually another indeterminate form on the right-hand side. What indeterminate form is that now? Infinity times 0. You see that? This piece would be 0. Natural log of 1 is 0. N goes to infinity. This is an infinity times 0. It's another indeterminate form. Okay? So in some ways, that's what I'm saying, that the 1 to the infinity could happen because of some rearrangement of something like this. Okay, now, I still cannot do L'Hopital's rule, right? It's supposed to be 0 over 0 or infinity over infinity. But we've said this before. I think I've said this several times before. If n is going to infinity, and I think about this number n, and this piece is 0, right, if n goes to infinity. I really want a fraction here, so why not this? Why don't I think about the reciprocal of n? Because what number makes the most sense to think about as the reciprocal of 0? Somebody said it. Infinity, and then vice versa, right? So if I would rewrite the problem this way. Now, algebraically, notice that this is the same. Like, I could say the natural log of 1 plus 1 over n over 1 over n. And this is still the natural log of L. Now, why did I do that? What's the advantage? Do you see it? Do you see it? I can now use L'Hopital's rule. Because if n goes to infinity, the numerator is still the same. It's 0. But if this n was going to infinity before, its reciprocal has to now be going to 0. So this is now 0 over 0. L'Hopital's rule applies. So can you figure out, remember here the goal was to know what L is. Right now, that's why I keep writing this, we are finding the natural log of L. So careful. Be sure you tell me in the end what L is. Take a minute at your table. Can you finish this? Okay, here we go. So, the natural log of L. The natural log of L should be 1 over, well, the limit, I should keep my limit. So the limit, n goes to infinity. This should be a 1 over 1 plus 1 over n. Chain rule, you're taking this derivative of n to the negative 1, so minus 1, n to the minus 2. That's actually what the denominator is, which means those should do that. And now if n goes to infinity, that part goes to 0. So this side ends up being the number 1. But that's not the answer. So what's L? L is E. So that means this. This is worth knowing. The limit as n goes to infinity of 1 plus 1 over n to the n is actually equal to the number E. So in other words, if you would take a large n, so if you say n is 100 billion and you put it into that function, you get a number close to E. Okay? The larger n is, the closer it is to E. So, nice review of some indeterminate forms, nice review hopefully of the comparing the rates of the functions, the relative rates of growth, the things we talked about last time. Okay. All right, moving on today. I've already said some of this, so I don't know if all of this really needs written down. But again, we have a series, which is a sum of a sequence. We have this sigma notation, and again, I'm writing this partly because these two things are saying the same thing. Okay, that's what the notation is saying there on the right. It means substitute in 1, substitute in 2, substitute in 3, and continue to do that forever. Notice on the left we have a plus dot 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 on the end, which means it doesn't stop. Okay. We have the terms of the series. So a sub n is the nth term. We could have the 7th term or the 12th term. But again, it's an infinite series, ... Okay. Again, I think that's kind of old news. So what we're going to do is we're going to start talking about convergence. Okay, convergence. That's a word you're going to hear me say a lot. And try to decide whether the sum of a series can be found. Now, we already know some of them that can be, right? Like the geometric ones that we've looked at. We're going to see those again today. Those couple formulas we had in the last chapter talking about that infinite sum of a geometric of A1 over 1 minus R, etc. All of that's still true today. So we know some, infinite geometrics would converge and some wouldn't, right? If R is in the wrong interval, it wouldn't converge. More on that today. But there's lots of series that won't be geometric that we'll need to decide whether they converge or not. So I've written something here like 2 minus 2 plus 2 minus 2 plus 2 minus 2. Now, sometimes when people look at that, they might say, well, the answer is 0, because they group the first two together, and then they group the second two together. Is that the only grouping that's possible? Or would a different grouping get a different answer? Can you think of a different grouping that would say, maybe it's not 0, maybe it's something else? Try that at your table. Think about that. Is there a different grouping? Some of you are talking about this. Like there's a different grouping, right? What if I group the second and the third one together, and then the fourth and the fifth? Well, those pieces would be 0, but I'm starting with the number 2. What do you think that says about this series? If a different grouping produces different answers, what do you think that's probably telling us about this series? No? Can you use some words? Can you use some words on your finger? I'm not sure what you mean. Okay? Yeah, there's going to be some bouncing around to this value, right? Plus 2, minus 2, plus 2, minus 2, right? So if it doesn't converge to a value, then it doesn't converge. So this wouldn't converge then, okay? Now, one way that we can show that is we think about the partial sums, okay? So partial sums. No, it's not. Yes, I know what you're talking about. So partial sums just means adding up part of the series, okay? So if I want the first partial sum, that would be, we label that S1. It just says, take this thing, add up the first term, so that answers 2. So I'm going to write that down. I'm making actually a new list, so 2. Now, let's find S sub 2. So S sub 2 is 0. What's S sub 3? It's 2. What's S sub 4? 0, and so on. So my partial sums are that. So how about this? If I want to know what the sum of this is, I'm going to put in symbols here something. I want you to think about why this makes sense. If I think about the nth partial sum, Okay? Like, I'm not going to put anything there right now. But do you realize this is either the number 2 or 0? Right? The way that I've constructed this. I don't know which one it is because I don't know if n is even or odd. But the sum of the series that I've started with, so thinking 2 plus, or 2 minus 2 plus 2 minus 2 plus 2, dot, dot, dot. That forever and ever. That answer must be this. The limit as n goes to infinity of that s sub n. Now, think about what we're describing here and why this really should make sense to us. Right? If I add up the first 5 terms, and then I add the 6th term on, and then I add the 7th term on, and if I make that larger and larger and larger, if this converges, shouldn't it be approaching some number, right, as s sub infinity, if I think of it that way? Should be approaching the sum of this entire list as s goes to infinity. Now, think about this setup. Does this have a limit for this problem? Will there be a limit that you could say the answer is 2 or the answer is 0? Do you know what this limit is? It's not a trick question. Do you know it? You don't. If this limit doesn't exist, this sum doesn't. So this doesn't converge because the partial sums, that limit doesn't exist. So that's what I've written down here at the bottom, okay? So since it's an infinite series, its sum has to be the limit of the partial sums. Since this has no sum, the series is going to diverge. I want to make a contrast here to this. I want to go back to one that we were sure converged and just see the difference here. So I want to start with this, like 1/2 to the n. Okay? I'll come back to the other statement in a second if you need it. Okay? But it'll make sense, I think, if we compare it. So 1/2 to the n. So let's think about writing this out. So this would be 1/2. So I'm looking at some summation here from n equals 1 to infinity. So this infinite thing. So I'm saying 1/2 plus 1/4 plus 1/8 plus dot, 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 forever and ever and ever. Okay? So let's think about the partial sums. So the partial sum, 1/2, that's the first partial sum. The second partial sum, what is it? 3/4. Add those together. Add the first 2 together. What's the third one? Come on, faster. 7/8. Next one. What is the next one? 31/30 seconds. Have you seen a pattern yet? That's interesting. So how about this? What does this sum equal? Because we know it's geometric, right? You actually know a formula because r is a half. You know this answer. We'll do the formula. A1, so the sum is something that's infinite geometric. It's this. What's r? What's this? It's 1. Now, what are you noticing? That if you're looking at these partial sums, do you notice that the partial sum is getting closer to this answer? In other words, 31/30 seconds is closer to 1 than 15/16, isn't it? And all of that's closer than a half. So notice that the partial sums are approaching the value for the limit. And that's not happening in the other problem, right? Our partial sums are 2, 0, 2, 0, 2, 0, 2, 0, 2, right? It's not approaching anything. So if the partial sums don't approach a value, then they don't converge. There is no limit to that. Okay? Does the contrast help? Okay. Something else. So here's an important statement. If an infinite series converges, it must be true that the limit as k approaches infinity of a sub k equals 0. And I want you to put a note next to this. This does not guarantee convergence. Or I could say this doesn't prove convergence. I'll tell you more what I mean by that. But effectively, here's what it means. If the terms of some series are not getting closer to 0, it can't converge. If the terms of some series are not getting closer to 0, convergence is not possible. But just because they're getting closer to 0 doesn't mean it converges. Did you catch that difference? So if something is doing this, if I'd say 2 plus 3 plus 4 plus 5 plus forever and ever and ever until the end of time, are we expecting that to equal a number? Right? We're not, right? So this is definitely going to diverge. Well, this statement is saying the only way that something could converge is if I'm looking at these numbers, it has to be getting closer to 0. Now, it has to actually just be getting closer to 0 at some point, because sometimes a sequence could like increase and then it starts decreasing. Like that's possible. But eventually, as I move further and further out, it's got to start getting closer to 0. So, example, think about what we just wrote. So, a half plus a quarter plus an eighth, plus a 16th, plus et cetera, et cetera, et cetera. That summation of that half to the n equals 1 to infinity. Do you notice that the terms are getting closer to 0? The sum isn't, right? We just said that the sum is going to be getting closer to 1, right, as I add them. But if I just say 1/16th, then 1/32nd, then 1/64th, individually those terms are getting closer to 0. So this says if it converges, that must happen. But that doesn't guarantee it's going to happen. There's a function, a series that we're going to see a lot that is worth mentioning right now. It has a special name. It's called the harmonic. The harmonic series. It's this. It's the summation from n equals 1 to infinity of 1 over n. So it's 1 plus a half plus a third plus a quarter plus a fifth, dot, 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 forever and ever and ever. Has anybody realized that their 89/Inspire will do summations? Anybody realize that? You can type in a summation to it. Now, it will actually let you type infinity because infinity is on the keypad in both of them. So you can actually construct a limit like this. But I'm going to maybe suggest an activity for you to play with. Now, the terms are definitely getting closer to 0. So before you type anything in, I want you to think about this. Ready? Do we think that this sum could get to the number 2? Do you think this sum could get to the number 2? 1 plus a half, well, that's 1.5, plus a third, plus a quarter. Can I get to the number 2? Yes or no? Sorry? So I can get past 2. Nene says I can get past 2. So if I go up far enough, well, can I get past 3? Or 10? Or 1,000? Have I made you uncomfortable yet? Well, we're going to be able to show that this diverges. And if I say it diverges, I'm actually saying that this sum is infinite. Now, on your calculator, you can play with this a little bit. I'll let you do that. I'm not going to do that right now. But you can find the summation, and if you put in this summation, like you could put a value here of like 10 to the 50th power or something like that for that upper limit, and see what it says. You might be surprised. I do have, I had Mr. Culbertson write a little program for me to do this, to show you graphically at the same time. It's actually, he turned it into an HTML for me, so I can show that later, but I don't want to get too far into the weeds to that. So we'll have a whole conversation later on about this harmonic and its peculiar behavior. The big takeaway right now is just because the terms are getting closer to 0 won't guarantee that it's going to converge. But if they're not getting closer to 0, it can't converge. So that's where, like, this we said converge to the number 1, right? Like, so convergence just means it should be approaching a value, one number, and that's why if we're going to say that the harmonic doesn't converge, it actually is going to infinity. For geometric, yes. Did you have more to say about that? If R is not between -1 and 1, what happens to the series? The terms do what? And the terms get bigger, right? They get closer, they get further away from 0 rather than closer to 0. So it's actually a connection to what you've seen before, right? So if I would say the summation from n equals 1 to infinity of 2 to the n, and so this is geometric, right? R is 2, so it'd say 2 plus 4 plus 8, right? If R is not between -1 and 1, this is just growing. This is exponential growth. I'm not going to expect there to be a sum here. Okay? So we've seen this already, and so it's a good moment to bring it back up, so thanks for doing that. Geometric is really this first term, so the book labeled it as A, but this, you could think about this as A1 over 1 minus R. We've actually already used this. Okay? But again, that's the whole point, because if the terms aren't getting smaller, that would be this scenario. Okay? Which is why we're saying a divergence. Oops, sorry. Am I good to go? On? You know this. You don't need this, do you? I don't think you do. Okay, so this series has another name, more generically. It's called a power series. A power series. It's a power series because it's based upon powers of x. It's power functions, right? They're not exponentials. When I think about that geometric thing, notice that here I've made an adjustment. This is worth writing down. This statement in terms of x's instead of n's, because we're going to see it this way more often, that this is geometric, right? Multiply by x. Multiply by x again. Multiply by x again. A1 is 1. Now, the way that I'm writing this is going to make you nervous in a second when I make a change here. You ready? Okay, you ready? Deep breath. Look at that equal sign, right? We're saying these things are equal. Now, they're not equal for every value of x, because this won't converge to that statement for every value of x. So we actually need to say here off to the side that this is going to converge. So this is going to converge when x is between what values? -1 and 1, okay? So between -1 and 1. Which means it's going to diverge on the values of the equal to 1 and -1 and outside of that. Think number line outside of that. That's the easy part. Ready? Do you realize what we're actually saying here is that this infinite polynomial is the same as that rational function on this interval? Let me say that again. that infinite polynomial, that's what the left side is, right? 1 plus x squared plus et cetera, on and on, forever and ever. That polynomial is identical to that rational function on the interval from -1 to 1. I'm saying identical because I'm saying ... If at any moment I do this and cut this off, and so I only have 4 terms, so this is also then true that 1 over 1 minus x should be about 1 plus x squared plus x cubed. Where? Here. Let me show it to you graphically. So I have a function, 1 over 1 minus x, right? That's what we have, a1 over 1 minus r. I have the first 2 terms here being written, 1 plus x. Now, I want you to notice the x equals -1. Maybe I should graph it. Like, look there, and then also look here, right? I'm looking between those 2 vertical lines, right? Because we're saying it converges on that interval. Ready? So here we go. If I add a term, so I now have h of x, which is x squared plus x plus 1, right? I've added one more. I've added the quadratic term. Do you notice that that parabola is fitting that rational function better? It's fitting more to this kind of interval from -1 to 1 than it was a second ago, right? If I back up, right? That line, locally linear, right? That's old news. That looks better. Well, doesn't this have to get closer and closer? Because if I add a term, shouldn't I be getting closer to what the sum is? So there's 20. There's 20 terms. 21 terms, actually, because it's degree of 20, I think, the way I set it up. I've lost track. It's too much on the screen. How does this show the interval of convergence? And that's the language we're going to use. The interval of convergence is the interval for which that sum produces an answer. So for us, that was between -1 and 1. So can you see visually the interval of convergence here? In other words, that the polynomial and the rational function agree on that interval. You see how close they are here? It's hard to see over here because this becomes an asymptote. Like thinking about this function, right? 1 over 1 minus x, it's an asymptote. So now this polynomial of degree 20 couldn't possibly become vertical, right? How do I know that? How do I know the polynomial can't be vertical? That would say it's undefined slope, but polynomials are differential functions, right? There's no asymptote in a polynomial function ever. So there has to be more to this curve, except it's just, well, it's got to get steeper, doesn't it? And so a higher degree would definitely get steeper and match it better. And if you don't think it matches well enough, then I just need to increase the power and match it better and better and better and better. Notice over here, though, on the left side, as we approach -1, do you see how it, like, the polynomial splits way away from that rational function? Okay. But it's happening closer and closer to the value of 1. So if I back this up, if you're looking right here, you should see that kind of moving back away. You see it? Diverges from the curve earlier. So here's what this means, and there is more to this in the next coming days, but it's possible to use a polynomial then to approximate really a lot of functions. In fact, We're going to see a really fun repercussion of it here in a few minutes. Promise. Let's go back here, take a few more notes. So, here's a power series. Those things are identical as long as we are on this. And again, I said it, but let me write it. This is referred to as the interval of convergence. The interval of convergence. It's the values of x where that statement is going to be true. And it's geometric, and so we knew that. So we're just actually writing that geometric in a slightly different way than we did before. Okay, so we're going to make new power series because we know that one. Okay, so if these two things are true, so maybe we should make an observation here before I do this next statement. If I say x equals 1/2, it's on the interval of convergence, right? So that would say 1 plus 1/2 plus 1/4 plus 1/8 plus ... is the same as 1 over 1 minus 1/2. And we did this one the other day, and you know that answer is what? I just wrote it. It's 2. 1 minus 1/2 is 1/2. 1 over 1/2 is 2. This is that 1 plus 1/2 plus 1/4, that thing that I was drawing the other day. So here's the point. I can substitute into this the way I could a function, and it will give me two representations for the same number. Okay? So if I can do it with the number 1/2, I can actually do it with a variable as well. So here's the first substitution we're going to make. I want to find a power series for 1 plus x. Okay? Using what I already know in that blue box. So if you look at the right-hand side of it, what value of x will then force me to write 1 over 1 plus x? What substitution could I make for x that's going to cause me to write 1 over 1 plus x? Yeah, if x is equal to negative x, if I replace it with negative x, if I make it its opposite, I would get that statement. So now do that same thing over here. What are you going to write? So x should become the opposite of x. So it should be 1 minus x plus x squared plus x to the fourth minus ... That pattern continues. So every x becomes its opposite. Okay, what's the interval of convergence here? Now, usually you can get that answer by thinking of the same substitution over here, right? So if you're going to get that answer of 1 minus x plus x squared by substitution, then the interval here has to also be by substitution. Well, if you rearrange that a little bit, what's the interval of convergence? It's the same values. So divide by -1, flip the inequalities. The interval of convergence here is going to be on the interval from -1 to 1. Let me try this one. Try this one at your table. So what do we think? So there's this kind of closed form of it. What would this side look like? 1 minus x squared plus x to the fourth minus plus ... so on, so on. So we're replacing every x with the opposite of x squared, right? Interval of convergence. Anyone? You got too quiet. Say again. Like that? Okay, do better though. Because the interval, I like how you're here at least, but the interval of convergence should be about x, not about x squared. Okay. Don't like that. Okay, it is I, but I don't like that either. Because we are talking here about some real value of x, and you actually did something wrong with part of this. It actually is plus or minus somewhere. How about this? Like this -1 piece of it, right? Everywhere from -1 to 0 is going to generate something that's imaginary to this anyway, right? So that can't be really where I should be looking. But if you look on the right-hand side of this inequality, doesn't it say x squared should be less than 1? Right? Isn't that what that's saying? X squared is less than 1? Tell me the values of x so that when I square it, I get a number that's less than 1. Not between 0 and 1. -1 and 1. So in fact, the interval of convergence is the same. It's -1 to 1. Take a minute at your table. Why is that still the same interval of convergence? It's sitting right here. This part's imaginary, but there really would be a plus or minus as you're solving that. X squared equals 1, x equals plus or minus 1. Take a minute at your table, talk about that. Let's look at this last one. So this one, I think I don't know where my writing just went here. Hang on, sorry. I'm on the wrong, there. So what if I want to find a power series for this one? Now, when we look at this, like this isn't just a substitution, right? In the last couple, like if we just make x the right thing and plug it back in, we can get this rational function that we see here. But for this one, we can't. But if we notice this statement, that the derivative of 1 over 1 minus x, if I would say take the derivative of that, so take the derivative of 1 minus x to the minus 1. Do you notice it's this? Bring the -1 down. There's no negative in the numerator because chain rule, right? Times another -1 here on the inside. And we would say this quantity to the -2, which is in the denominator. So, okay, so the derivative of, if I zoom out here a little bit, the derivative of this is the thing I want. Oh, don't we actually know what we need to do then? If these two things I circled are equal, they're functions, right? And they're equal to each other. Well, shouldn't the derivatives also then be equal to each other? What are you going to write down? Do it. If these two functions, if the pink is the same as the green, shouldn't the derivative of the pink be the derivative of the green? And if the derivative of the pink is that, then what are you going to write here that it must be equal to? So 1 plus x plus. And that is an equal sign. I don't know why it looks a little wavy, but that's an equal sign. Taking the derivative isn't going to change where it's convergent. It's going to be still here convergent from -1 to 1. Everything here is power series, yes. So we're going to see other things that aren't power series. All right. Put a star next to this one. This one. That's going to be one that is worth paying attention to. A lot of times people remember the ones above by substitution. So notice that this is not exactly geometric any longer. Do you see it? We kind of broke the geometric thought. So really everything else has a geometric thought still to it, right? We can find the r, we can multiply by r again, and get different answers. The moment I take the derivative, I have something that is kind of geometric, right? It's still a times x. I wrote something wrong. Yeah, I don't know where that came from. Sorry about that. So that should be the derivative of 1, the derivative of x squared. It's probably series fault. Just kidding. So, yeah, sorry, you should have stopped me sooner. But so it's kind of geometric, right? There's still this kind of times x, but the coefficients aren't really matching what you'd expect, right? There's not a multiple that's going to take them to each other. So that's worth noting, that things that kind of look geometric are maybe the derivative of a geometric. Okay. So interval of convergence here, I said it, but it's from -1 to 1. Now, in the last 15 minutes, I want to show you something interesting about this. Fun, even. Yes, question before I do that. Like that pink part? Yeah, really, we're saying that all of these that we've looked at here are related to that first one. So either by substitution or by taking the derivative, we get other statements that then are true on some interval. Maybe not true everywhere, but true on some interval. Okay, so I want to go to this one for a minute. Okay, so jot this one down. You need a little space. We just wrote this one down, didn't we? Right, there's a substitution. This is the one that should converge from any value -1 to 1, because if x squared is less than 1, then x is between -1 and 1 still. Okay, so this statement is built off of that geometric that we have already worked with and used. Okay, so again, I am saying the thing on the left and the thing on the right are the same. Well, if I could take the derivative, then I should be able to think about antiderivative. you weren't supposed to see part of that. Maybe you didn't notice. Now, it's all addition and subtraction on the right-hand side, so shouldn't I be able to, like, instead of thinking, like, integrate this entire side, find the antiderivative of that entire side, couldn't we find the antiderivative of each of these separate pieces? And that's really not difficult. We've actually been doing that, right? Antiderivative 1 is an x. Then I'd have an antiderivative, and then the antiderivative, and then antiderivative, so on and so on and so on. Now, sometimes people start getting nervous about all of the constants, right? Wouldn't there be constants involved here, right? Because I don't know that antiderivative. Now, there would actually be a constant really on both sides. And I can really think about it as two constants, right? There's one on the left side and one on the right side. Now, because even if I say that this integral generates a constant and then this one generates a constant for the x squared and so on, can't all the constants be put together on that right-hand side? So I don't really have to worry about the constants here. More on that maybe in a minute. Do you recognize that antiderivative? Do you know what function we must be talking about there? Can you tell me the function that if I take the derivative, we would have said that? Not 2 over x. Try that. What? I didn't get all that, John. It's not a natural log, because if you try that, you can get that part, but then you get a chain rule with the two x's. We don't have that. Vallejo? It is the inverse tangent. Okay, it's an inverse tangent, which means, well, because the derivative of the inverse tangent. Okay, well, hang on. So all of these antiderivatives here are easy, aren't they? Like the antiderivative 1 is x. The antiderivative here is x cubed divided by 3. X to the 5th divided by 5, right? And on and on and on. Dot, dot, dot. Now, this also is going to have an interval of convergence that's going to be the same, which shouldn't surprise us because it's all based on, this one had an interval of convergence from -1 to 1, so why would integrating produce a different interval of convergence? It won't. All right, so what if x is 1 over the square root of 3? Now, notice in some ways that we don't really even have to worry about this constant, but inverse tangent is this. What if x is 1 over root 3? So notice that that is a number between -1 and 1, right? 1 divided by a number bigger than 1 has to be less than 1. So what would I write? So I would write the inverse tangent of 1 over root 3 is 1 over root 3 minus 1/3 times 1 over root 3 cubed plus 1/5 times 1 over root 3 to the 5th, dot, 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 forever and ever and ever. And you look at this and go, I don't have any idea why you're doing this or why this is interesting. What is the inverse tangent of 1 over root 3? You know it. It's on the unit circle. It's inverse tangent, so I would like it in radians because remember that derivatives and antiderivatives are only true in radians, right? So we should be thinking radians here. I hear pi over 6 because somebody typed in their calculator. Is it pi over 6? It's pi over 6 or it's pi over 3. I don't know. You've got resources. Figure it out. Don't wait on somebody else. I've got time. Is it pi over 3 or is it pi over 6? It's pi over 6? Are you sure? Yeah. Okay, well, if this is pi over 6, then this is pi over 6, right? Wait, do you realize what this means? That pi equals 6 times 1 over root 3 minus 6 times 1/3 times 1 over root 3 cubed plus 6 times 1/5 times 1 over root 3 to the 5th. Pi is actually the sum of that series. Fun, right? Well, it'd be pi over 6 right here in that step. So that's why I'm multiplying. I'm basically multiplying both sides by 6 and then distributing that 6, and that would get me what pi is. So that is true that initially we are getting actually the value of pi over 6, but that's why I'm saying rearrange it here. That's what these 6's here. I'm distributing that 6 to those terms. Okay? So this is actually one of the ways, what you saw right here. Have you ever thought about how they know more digits of pi? Or how about this? Do you notice that if I'm wanting something closer to pi, I could always just add another term? Do you see why I'm going to have trouble having a closed form of this number, maybe? But anyway, that's really what's happening. This is one of the computer algorithms that's used to generate more digits of pi. Why is tangent special? I don't understand the question. Like, how did that even happen here? Okay. Okay. Well, it's just an observation that if I choose, this is actually how you think about, like if I just go back to unit circle here, are we listening? Can we listen, please? Listen, listen, listen. If I go back to unit circle and I do this, and I just think about that this point is root 3 over 2 comma a half, and I think about tangent, like really that should be opposite over adjacent, and that's really 1 over root 3. So you could have also said root 3 over 3, which would have been the same thing. I just left it this way. So it has to do just trig functions back here at the unit circle. So, big ideas today. We should be able to take a series, a power series that we know that's geometric, and manipulate it and make new ones. They are not going to converge everywhere. And again, that's this image, right? We're not saying that the polynomial is identical everywhere. but it's identical from the interval of convergence. Now the last thought here, I want to show you something that's very different. Very different. Okay. Jot this down. We got 5 minutes. We can do it. Suppose. Remember, factorials are defined 2 factorials, 2 times 1, 3 factorials, 3 times 2 times 1, 4 factorials, 4 times 3 times 2 times 1, etc., etc. Do you realize what the derivative is yet? Work faster. You can do this in your head. Promise. Definitely is not undefined. Simplify that. Focus, focus. Who knows what it is? Henry says it's this. Henry, how do you see that? Explain. Okay. Yep. Threes cancel. Yep. 2 factorial. Do you see it? Oh, wait. Wait, that means something. That's super special. We've only seen one function that ends up being its own derivative. E to the x. So e to the x must be 1 plus x squared plus x cubed, 3 factorial, plus x to the 4th, 4 factorial, dot, 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 forever and ever and ever. I want you to see it graphically. So here's e to the x. I'm going to think about 1 plus x. Okay, so that's the first 2 terms. It definitely fits really well in here around 0, right? So my question is, what does it appear that the interval of convergence is? What do you think it is? Do you see how this is really different than the one I showed you earlier? As I showed you earlier, it just kind of like got stuck and it just tried to go up, faster, but that's not what's happening here. The interval of convergence is all real numbers. Here's what that means. Last thought then. So interval, negative infinity to infinity. And so that means if you want to know what e squared is, so the number, e times e, must be 1 plus 2 plus 4 over 2 plus 8 over 6 plus dot, 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 et cetera, et cetera, et cetera. You just substitute in a 2 everywhere you see an x. You want to know what e to the first is? If you want this number e, this 2.718281828 dot 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 forever and ever that we don't understand that well, but it's actually the number 1 plus 1 plus a half plus a sixth plus a 24th plus dot 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 forever and ever and ever. Just substitute a 1 everywhere on the right hand side. This is the number E. 2 transcendental numbers for you today, E and pi, written as a series. You should have some homework. This is 10.1. There is a test for the first things that we've done. That is take home. That is posted. The calendar doesn't show when it's due, but my math lab, if you look in the assignments, does. Work on that. See ya. Have a good night. A series? You can title your notes to say power series, because these are powers of x, right? So there's power functions. That's what you ought to call it.